Hi everybody, in this video I want to talk about P and NP and then define NP complete and NP hard. We'll take a look at the traveling salesperson problem and then we'll talk about approximate solutions to traveling salesperson. So we've talked about this already, P versus NP, but now I want to go over it again just to give you some review and to provide some context as to why we're doing it. So we have mentioned this, that X is an NP if and only if a solution to X can be verified in polynomial time on a deterministic Turing machine. So given a solution to X, we should be able to verify that it is correct in polynomial time. This is sort of equivalent to guessing a path through a non-deterministic Turing machine. This should remind you a little bit of what we did with NFAs, because if you think about an NFA, you can take all the branches and look at whether one of those paths accepts. So Turing machines, when we went back to those, we said there's not really a difference in terms of decidability of the problem, but we do have a difference in terms of the complexity of the problem. Now, for the set P, it's pretty easy to be told which path it is non-deterministically. There's literally only one. So the set NP contains the set P. So let's ask ourselves the number of steps that it would take to solve a problem. If you wanted to solve a problem X and it had some sort of parameters that were of size n, if it's polynomial in n on a deterministic Turing machine, then X is in P. If it's polynomial on a non-deterministic Turing machine, then X is in NP. Now, X may or may not be in P, we don't know. Now, to verify a solution to a problem, you're just basically told that path. So if it is polynomial in n on a Turing machine, then X is in NP. So these definitions are going to apply to the best known solution for X. Classification is based on the best known solution. So NP problems, you can kind of see here with this picture that the problems in P are a subset of NP. Now, a problem is definitely in P if we know a polytime algorithm for its solution. A problem is in NP, and maybe it's in P if there's a polytime verification algorithm, but right now there's no known polytime solution algorithm. So this is kind of weird because it's like I don't know if it's in P or not, just because I don't know if NP is equal to P. Now, if you started finding polytime solutions to problems in NP, then it would mean that P was equal to NP. And that second bullet that I have here for you, where I've said, oh, it's maybe in P, now we know that there is a polytime solution for it, and it would be in P. This is the most famous open problem in computer science. Is it the case that P is equal to NP, or is it the case that P is a proper subset of NP? Now, we believe that it's unlikely that they're equal. Just with conventional notations of computing, it's unlikely that there are undiscovered polytime algorithms. And if P is equal to NP, then a number of other unlikely results are true. But, I mean, this is really just our feelings about it. But people do have a lot of strong opinions about this. Scott Aronson says if P is equal to NP, then the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Okay. And being attached to a speculation is not a good guide to research planning. That's what Anil Narodi says at Cornell University. I think this is the Narodi from My Hill Narodi. So if it did turn out that P was equal to NP, I guess people would be sad. And then there are some implications. Many problems that we considered intractable would be within reach. And that includes cracking public key cryptography. So public key cryptography relies on the fact that we don't know that P is equal to NP, right? And hopefully that it's not. And all of privacy and trust on the internet is based on that. If it turned out that P was equal to NP, everything would collapse on us, and we would no longer really be considered to be secure on the web at all. Your passwords would no longer be any good. It is actually true that, for instance, the RSA problem, if you're familiar with that, is breakable in polynomial time on a quantum computer. So there's been work towards using other hardness problems. So things like that did actually affect what we are doing in the future. What RSA, this is all, P and NP, by the way, are defined on classical computers, not on quantum computers, so that does make a difference. All right. There are also problems in chemistry and biology that are extremely difficult to solve, folding proteins and things like that. Since we can't do those fast right now, it actually slows down our ability to, develop new paints or medicines or whatever is going on. So if we were able to get P is equal to NP, some polytime solutions, we would all of a sudden have rapid advances in these fields for certain problems that they're doing. It also means that it would be possible to find and verify proofs in mathematics a lot faster. Okay, so now that we've talked about P and NP, and we agree that we are ignorant and we don't know that P is equal to NP or not, let's talk about other sets of problems. So I've drawn the picture here as P being a subset of NP, and at the top of NP I have this thing called NP complete. So above that I have NP hard. Now if we assume that P is not equal to NP, then there is this concept of a problem being NP hard, which is a special type of problem where if you could find a solution to X, it could be then used to solve all the problems in NP. There is no requirement that an NP hard problem have a polytime verification algorithm. For example, think about this as problems being harder or easier. Let's say that you could find roots of a cubic polynomial, then perhaps you could use that to find the roots of a quadratic polynomial. And it's way easier to find the roots of a quadratic than it is for a cubic. But anyway, now there are some special problems, NP hard problems that are in NP. These are going to be the NP complete problems. Let's go back to traveling salesperson. Now, we have talked about the decision version of traveling salesperson. Let's now talk about the finding, optimization version of traveling salesperson. Here you're just given a graph and you're just told find the shortest tour. Now, if you're just being asked to find the shortest tour, it turns out that TSP, that version of the problem, is not even in NP. So this is a different kind of problem entirely that's harder than the one that we've talked about before. And the reason for this is if you are just told this is the shortest tour, you have no choice but to check literally all of the other tours to make sure they aren't shorter. If you are told something like, oh, this tour is less than 700 miles, you can believe that and just check that one tour. But if you're told it's the shortest, you don't get a break, right? And we talked about this previously where we said, okay, if you follow a path down, you can check if it's true. And in this case, you would have to check all paths. So this problem is NP hard, the optimization version of the problem, right? Different from the decision version. Now that means that a TSP solver can be used to solve any problem in NP. We're not going to show really how to do this, but it is possible. We'll see some other kinds of reductions elsewhere in this class. As I mentioned, the brute force version of TSP is to check all O n factorial permutations of the nodes. You can do a dynamic programming approach to TSP, which is O of n squared 2 to the n time complexity. Now, there is no way to verify the candidate solution in polynomial time if we are looking at the optimization version of the problem. You have to check it against all the others. This is different from the decision problem. So let's continue talking about optimization. Now, like maybe we just care that our path is less than 700, but probably we really, really do want the best version of the answer. And traveling salesperson has practical importance. So we have come up with these ideas of approximation algorithms for it, where we can say it's at least this good. Some of the applications of traveling salesperson include planning and logistics, and even the manufacturing of microchips, DNA sequencing. So the concept of city and distance mean different things in those contexts. If you ever take the AI course, which I think is CSC 411 at NC State, you might learn about robot planning, which would be some applications of TSP. Now, because we have these varieties of TSP, we can think about not just general graphs, but maybe embedding it on like a Euclidean plane, like XY axis. Even that version is NP hard. And then, as I've mentioned before, the TSP decision problem, which takes in G and some threshold distance D, is NP complete. There are a bunch of other variants, symmetric, asymmetric, bottleneck, which we won't really talk about too much, but I do want you to be aware that there's so many versions of this question. So let's get back to solving NP and NP hard problems in general. If the best known algorithm requires more than polynomial time, what do we do? We're just going to approximate. Approximating means solving a different but related problem. And so, for example, the TSP problem might say find the tour, and it doesn't have to be the shortest one, but it's at most 2 times the shortest one long. If you're doing package dependencies because you care about NPM and open source security, by the way, you should take CSC 405. Package dependencies becomes find a set of packages that satisfies the need of package X, even if that set is not the smallest set. So we have this concept of a provably good approximation, which is what I've already mentioned. It's like, oh, it's at least like no worse than 2 times the best solution, no worse than 3 times the best solution, something like that. So we are going to have a guarantee here, an actual guarantee. So a provably good approximation to a problem computes an answer that is within a known factor of the exact answer and has to be efficient, right? So getting 2 times TSP can be done in polynomial time. You might be, if you're interested, you can go to Wikipedia. You can learn about the Christofides algorithm. This one's better, and it's 1.5x for Euclidean TSP. In this case, the error is bounded, and we have to prove that it actually has that optimization associated with it. That proof is the guarantee that the amount of error is limited. So another concept that I want to tie all of this back to is when we write algorithms, we also want to prove that it has some properties. Here's my algorithm, here's that it's correct, and here's its runtime. And here is some other bound now, like the error bound, that I want to prove about it. This is going to be a general thing that you're going to see all throughout your life as a computer scientist, because you got to write algorithms and then you got to say something about what they do. All right, we don't need to read all this, but here are some little screenshots from the Christofides page, which, if you're interested, you could go ahead and read. The other approach is heuristics, which is just fancy guessing. Heuristics don't give a guarantee of answer quality. It computes an answer efficiently, but no guarantee on accuracy. So it's just you get some answers and IDK, maybe it's okay. So there are greedy algorithms for TSP, like nearest neighbor. It might be just the case that on average, it ends up doing a good job. But the error is actually unbounded. And there are these pathological cases where the heuristic does very poorly. Now, in reality, we're doing cities and distances, or package management, or DNA sequencing. And so most of the instances of those problems are not going to be so nasty, but sometimes they are, right? That's what I call these pathological cases, sort of like halting problem. Like, yeah, I guess like most Turing machines, that, many that we work on, they do end up being solved in some amount of time and they're decidable. But here are some nasty cases where it doesn't work. And here are some more realistic cases where it doesn't work. Having some ideas about where those things are and whether those cases are truly pathological or whether it's a common thing to find is also important to your development as a computer scientist. All right, I'm not going to go over this, but there is a greedy algorithm for TSP, which we might come back to later. Okay, so back to this picture. NP complete is the next important set of problems. If a problem is both NP hard and it is an NP, then it is called NP complete. The canonical NP complete problem is the language SAT, which is satisfiability, and phi is a satisfiable Boolean formula. The question becomes how to verify a solution to a formula like phi is equal to x and y, or not x and z. The input size of phi is the number of variables that you have, so x, y, and z in this case, which would be 3. And then think about the truth table. It's going to be 8 rows long because you have to do all the combinations. That ends up being exponential. So, at first glance, trying to solve a SAT problem involves calculating out the whole truth table, which is exponential. But if I wanted to verify the solution was correct, it would only take me polynomial time because I have, n many variables, and verifying that the formula phi ends up being true overall will only take me polynomial time. So that means that SAT has a polytime solution verification algorithm on a deterministic Turing machine. And that means that SAT is in NP. This is going to be true of any problem, but if it has this polytime verification algorithm on a deterministic Turing machine, then it is in NP. Now, I kind of mentioned this already, but how hard is it to solve SAT? If you have really simple formulas, you can do it in polytime, but in general, this is not the case. So you might have to try every possible assignment before you win. Now, weirdly enough, most problems are either in P or are NP complete. So a lot of problems that we care about in graph theory or other algorithms end up being NP complete if they're not in P. This actually means that if we find an efficient solution for one, they all end up falling and become efficiently solvable, and then I would collapse this hierarchy here. Efficient for us is going to mean polynomial time, and we have this concept of polytime reductions. Okay. There are a bunch of other classes that are worth kind of knowing about at some point. They are interesting. Sometimes we don't care about time, but space. So, for instance, there's P space and N space, which is like if you need to store data. And then there's X time at the very top, which is 2 to some big number here. So you might be interested in things like probabilities as well. So if you care about probabilities, then you might want to use probabilistic Turing machines. You might use Arthur Merlin proofs, which are important in cryptography. P-space and IP, which is interactive proofs, those are also important in cryptography. You might also be interested in counting problems. So we use this sharp P symbol, which you might read as a hashtag, but it's sharp P to indicate like being able to count solutions. You don't need to memorize all these, but I want you to be aware that there is like a whole zoo of complexity classes out there. All right, so um, CS is a science. It's based in math, though, right? So we came up with computer science long before there were what we think of as computers today. Turing did all of his stuff on paper and mechanical computers. A literal person can be a computer. It has this theory that goes with it, and it has predictions and limits. It's still developing. And as Ada Lovelace says, the science of operations, as derived from mathematics more especially, is a science of itself and has its own abstract truth and value. So I really do want to encourage you to go out there and become truth seekers and, at your job say things like, well, is that true? Can that actually happen? Is that problem impossible? These are real things that are going to happen to people that work in computer science jobs, like as in software development, even if it doesn't seem immediately obvious. I did want to take a time here. I'm encouraging you to be truth seekers, and let's think about all that we've done. We've started with finite state machines, went to push-down automata. We talked about deterministic push-down automata, and then we talked about Turing machines. We also briefly mentioned linear bounded automata. There's a lot in the world here because we talked about decidability, recognizability, and all this kind of stuff. Having the ideas of all these types of simple machines really puts it into context what we have done with computing overall. And I hope that you can appreciate these tiny little building blocks that make up what it means to be a computer scientist, like really be a computer scientist. All right, so thanks for watching this video. We are going to expand on a couple of these topics throughout the course. Depending on where you're watching this, when you're watching this video, you might remember that there's a reference to a lecture in the past about this, or perhaps you haven't seen it yet and we'll see it in the next week. And I do like to show you things at least a couple of times so that it really sinks in. If you haven't seen it already, again, depending on when you're watching this, reductions are going to be really important for us, and approximation is going to appear again as well. But I'm really into reductions as a cryptographer, so we're definitely going to see that again. But for now, thanks for watching.